In this presentation, we'll explore interdigitated electrode sensors. These devices are widely used in chemical, biological, and environmental fields because they convert subtle physical or chemical changes into an electrical signal. The goal is to understand how they are built, how their electric field works, and why their geometry plays such a key role in sensitivity. This video has been produced within the framework of the European project titled Personalized Education in Measurement Science and Technology Empowered by Machine Learning. Interdigitated electrodes, or IDEs, are planar microelectrode structures composed of two comb-shaped metallic electrodes interlaced on an insulating substrate. They operate as transducers, meaning they convert physical or chemical changes in their environment into measurable electrical signals, typically impedance or capacitance. Because of their high surface-to-volume ratio and the ease of miniaturization, IDEs are widely used in fields such as biosensing, corrosion monitoring, humidity and gas sensing, and microfluidic systems. The planar interdigitated sensor interacts with the material under test from a single side of the substrate. This makes it easier to integrate since you don't need access to both sides of the sample, unlike traditional parallel plate capacitors. This fringing field is what makes IDEs so powerful for non-destructive dielectric measurements. Any change in the physical, chemical, or structural properties of the medium that alters its permittivity will be detected as a change in capacitance. Finally, the sensor's geometry, i.e., finger spacing, width, number, etc., controls the effective field penetration and thus the sensitivity. When we apply different potentials to the two electrode combs, electric field lines travel from one finger to the other through the sensing medium. The versatility of IDEs comes from the fact that any local, physical, or chemical variation alters this field. When the medium changes, for instance, when humidity increases, when ions accumulate, or when a thin sensitive film reacts, the field distribution changes. As a result, the capacitance or impedance measured between the electrodes also changes. This enables non-destructive measurements and makes IDEs well suited for surface and interface analysis. A planar IDE sensor is formed by a pair of comb-like electrodes on a substrate. Contact pads are used for wiring. The sensor geometry is characterized by the number and length of the electrode digits, their width, and interdigital spacing. Penetration of the electric field under applied potential is approximately equal to the distance between the centers of the electrode digits, so the current flows close to the sensor surface. Thus, the miniaturization of the electrode width and the spacing between the electrodes allows for an increase in the sensitivity related to reactions occurring on the sensor surface. IDEs can be made from several conductive materials depending on the application. Gold is widely used because of its excellent stability and biocompatibility. Platinum offers similar advantages and is suitable for more demanding environments. Silver and copper provide high conductivity at a lower cost, but they can oxidize, so they often require protective coatings. Finally, carbon-based inks are increasingly popular in printed and flexible sensors due to their low cost and good electrochemical behavior. Substrates define the mechanical and fabrication characteristics of the IDE. Glass and silicon offer excellent dimensional precision and stable dielectric properties, making them optimal for laboratory and microfabricated devices. Ceramic substrates like alumina are used in gas sensors, where the device operates at a few hundred degrees Celsius. These sensors often include a small serpentine heater on the back to maintain the required temperature. Polyamide enables flexible and wearable applications thanks to its thermal and mechanical robustness. PET and PEN provide an affordable alternative when transparency or disposability is important. More recently, paper-based substrates have gained interest for sustainable, ultra-low-cost printed sensors. Printing has become one of the most promising routes for fabricating miniaturized and flexible interdigitated electrodes. It allows high precision at low cost, minimal material use, and compatibility with flexible substrates. Non-contact techniques like inkjet, slot die, and aerosol jet offer precise patterning, while contact methods such as screen, graver, and flexographic printing are ideal for scalable production. These approaches are key to developing flexible IDE sensors for biomedical and point-of-care applications. Depending on the sensing principle, IDEs can be amperometric, detecting current from electrochemical reactions, potentiometric, measuring voltage changes, conductometric, sensing conductivity variations, or impediometric, analyzing frequency-dependent impedance. Among these, impediometric sensing using EIS offers detailed information on electrode interfaces by characterizing resistive and capacitive elements and dynamic processes such as diffusion. Electrochemical impedance spectroscopy, or EIS, is one of the main characterization techniques for interdigitated electrodes. In an EIS experiment, we apply a small sinusoidal voltage and measure the resulting current response. Because the current and voltage can be out of phase, the impedance has both real and imaginary components, reflecting resistive and capacitive effects. We can plot this data in two ways: the Nyquist plot, showing the imaginary versus real impedance, or the Bode plot, showing impedance magnitude and phase as a function of frequency. The data are interpreted using an equivalent electrical circuit, composed of elements like solution resistance, Rs, double-layer capacitance, CDL, and charge transfer resistance, RCT. In this example, we see that at high frequencies, increasing salt concentration decreases the Z, i.e., the resistance, because the solution becomes more conductive. At high frequencies, the response is almost purely resistive, while at lower frequencies, capacitive effects emerge. This simple case clearly shows how IDEs can detect even subtle changes in the surrounding environment. Thank you for your attention. This video was produced through the collaboration of SS Cyril and Methodius University of Skopje, the University of Niš and Politecnico di Milano, within the framework of the European project Personalized Education in Measurement Science and Technology Empowered by Machine Learning. More information about the project can be found on the project website and LinkedIn page.